So let's do example 16.7. All right, you're going to find that it's pretty similar vector-wise to the force example, where we found the force due to three charges, or the force on a charge due to two other charges in a plane. So we're going to approach it in the same way, except we need to use the expression for electric field and use the rules for electric field to determine the directions of the field. So this is also another difference is that this is going to be, you know, purely algebraic problem. Everything is in terms of Q or D or R. So your result will be an expression, not a value. So what we need to do, so let's look at the question. What's it asking? Here's the setup, right? Positive charge on the left, negative charge on the right, and then at the vertex, the other vertex of the triangle, we have a point P. Derive expressions for the magnitude and direction of the net electric field due to those two charges at point P. And the distances are given here. This distance is R, which I imagine we're probably going to express in terms of Y and D, okay? This Y is the height of the triangle. D, or 2D, is the distance between the two particles. So let's first find the magnitude of the electric field. So that was the approach in the force problem, and let's take the same approach here. Let's find the magnitude of those two vectors, and then we can find the components of the vectors, okay? Because in the picture, it looks like we already have, you know, let's erase it and start over, right? Right, they already gave you the directions of the electric field. Let's pretend like it's not there. Oops, I just undid that. Okay. So what direction, okay, so I said we're going to do the magnitude first. Let's find the directions first. Let's just talk it through real quick. All right, let's start with negative Q. Negative Q is producing an electric field. We want to know the direction of that electric field at point P right here. Okay, the rule is that electric fields, E fields, always point toward negative charges. So the electric field direction would point on a straight line path directly toward the negative charge, starting at point P. What about the positive charge here? Well, at positive charge plus Q is producing an electric field, and that electric field exists everywhere in space. We are concerned with where's the electric field pointing at point P due to the positive charge. Well, the rule for positive charges is that E fields always point away from positive charges. Okay, so starting at point P, we're going to draw a vector, straight line path directly away from Q. And so now you can see, now you can see those E vectors. They make sense why they're there. And so what we're going to do, we're going to find the magnitude of those vectors and then find the components of those vectors. And so the magnitude of the vectors, well, they're going to be exactly the same because these charges have the same magnitude but opposite signs. So the magnitude of the E field is going to be K Q over R squared, right? Where Q has the magnitude bars on the other side to let you know to drop the negative sign. So E plus, the magnitude of E plus is going to be KQ over R squared. And that's going to be the same as the magnitude of E minus. Okay? And so R is not like a variable. I mean, it's a variable, but it's not a given in the problem, right? It's not a known. Technically, 2D and Y are the knowns, okay? Right? They're providing that to us. This R here is just to describe the distance between the point and the charge. So what we should do is we should express R in terms of the givens in the problem, Y and 2D. And so we can use Pythagorean theorem to do that, right? This is a right triangle right here. So, right, that's a right triangle. So Let's find out what R is. So R is the hypotenuse of the right triangle. Y is the height. And then what is this side? This is D, right? Not 2D, but D. That makes R equal to y, square root of y squared plus D squared. So we can plug that in here. That whole quantity is squared, which just gives us back this R, y squared plus D squared. So there's our magnitudes, okay? There's our magnitude of E. So, and we see the direction. So let's draw a little picture of the components. Let me go ahead and copy this image down below. I don't like, there we go. Let's copy it. Let's draw our components, and we'll use the method of similar triangles to find the component directions. You may be able at this point to look at it and, you know, by inspection, figure out what they are, but we'll do it the long way. So so first, you know, we need to find the components in the X and Y direction. So I'm going to draw my X and Y axis here. Okay, here's Y, here's X. And so we need to find the X component of E plus and the Y component of E plus. And then for E minus, the X component of E minus and the Y component, let me write that over here, and the Y component of E minus. So looking at this picture, we can actually do the math because, number one, the distance between Q plus and P and the distance between Q minus and P are equal, okay? And then number two, because the magnitudes are equal, that means that these components, E plus and E minus Y, are going to be equal as well, okay? So we can actually look at this picture and do the math in our head and say, guess what? E plus Y and E minus Y, they're going to add up to 0, so I'm not even going to worry about figuring them out, okay? Who cares? Who cares? Let's save ourselves some time, right? So all we need to do is figure out what E plus X is and multiply that by 2. You see what I'm saying? So all we need to figure out is, you know, what is E plus X? So our similar triangles, let's draw them. So here's the first triangle, the one with the knowns, right? This is R. Well, this isn't R. This was Y squared of Y squared plus D squared. This height was Y, and this guy was D, right? So this is our knowns. And then in the triangle that forms the components of E plus, these are technically our, you know, the unknown, right? This is the unknown. We want to find this. So we'll use the law of similar triangles, which states that, you know, the ratio of the sides are equal. So the ratio of these two sides should equal the ratio of E plus X to E plus. Okay, so we can solve for E plus X, which is our unknown. I'll put parentheses there so we don't get confused, because that's a subscript. D square root of Y squared plus D squared. And so now we can plug in what E is. E plus is this guy right here. kq over y squared plus d squared. Right, that's E plus. And then times all this junk. And we do a little bit of algebra. Let me scoot that so it's more clear. Right, we do a little bit of algebra. This is, you know, y squared plus d squared to the 1. This is y squared plus d squared to the 1/2. You add those together, the exponents that is, so you get k q d over y squared plus d squared to the 3/2. That's your E plus x. We're not done yet. All we found was this guy. The question is, what is the net? Sorry, that's my dog wanting to play toys if you hear like weird noises. This is my dog. You might have seen him in the welcome video. It's Lando. What is the net electric field? Stop, I'm trying to write, buddy. Electric field at point P. Okay, so the net electric field at point P, well, what we need to do is we need to add E plus to E minus, which means we need to add their components, right? So if this is the X and the Y components, remember the components can be positive or negative, right? So let's take a look. The X component of E plus is positive because it's pointing to the right. Let me get my laser pointer. Okay, pointing to the right. The Y component of EY is pointing up, so they're both positive. So let's go ahead and write and then let's look at E minus, the components. The E minus X is positive. The E minus Y is negative. So when we add these up, this becomes 0. This becomes E plus X plus E plus Y. And what we, by this argument right here in the red, I told you that all those components are equal, right? So this ends up being 2E plus X. And that's the total. That's the net electric field right there. So here's E plus X. We need to multiply that by 2. And when we do, we get 2kqd over y squared plus d squared 3/2 in the x direction. Okay, that's the total. That would be E, you know, the net electric field. Okay, and it's positive. It's in the positive direction. So we can see that, right? These guys go away. And the only components left in the vector are the positive x components for both. And you add them together to get a vector that's twice as long. Okay, so we did a lot of, you know, conceptual work in order to reduce the math work that we had to do, right? We could have done the long way, which I like to call the pedestrian way, right? Like you're just wandering around and you're doing a lot of math and you're walking. We could have done, you know, the law of similar triangles for E plus Y, E plus X, E minus Y, E minus X. We would have done this 4 times, right? And then we would have seen the minuses and the pluses add together or add to 0. We would have seen that. I gave you some arguments here, argument 1 and 2, that allowed us to, you know, to forego doing the pedestrian route and doing all those calculations and skip straight to just calculating one component. Okay, So that's the shortcut way to doing this problem. If you take a look at the slides, I think they do it in a little bit longer method, okay? So take a look at both if this method confused you and why and how I used argument 1 and 2 to reduce our work. All right?